Hello and welcome to some more reinforced concrete design. In this session, we will be discussing the shear between the flange and the web in flanged beams. To understand why the longitudinal shear develops, we consider a segment of a flanged beam with a length of delta x. Sagging bending in the beam results in the development of compression stresses in the flanges and the top part of the web and tension in the bottom part of the web. Since the flanges are much wider than the web, the compression forces developing in the flanges are larger than those developing in the web. Let's now consider only the compression forces Fd in the flanges of either side of the web, which is balanced by the tension force 2 times Fd at the bottom of the web. Since bending moment changes over the length of the segment, the compression forces in the flange will change by delta Fd, while the tension force in the web will change by 2 times delta Fd. The equilibrium of forces of the entire beam segment shows that there are unbalanced tension forces, delta Fd, in each flange, and the unbalanced compression force, 2 times delta Fd, in the web. These forces want to move the web and flanges in different directions, and should be transferred between the web and each flange through the 2 planes connecting the web with the flanges. As we saw, the change in bending moment in the sagging zones results in the development of unbalanced compression forces in the flanges on either side of the web and an unbalanced tension force in the web. A similar effect also occurs in the zones of hogging bending, where the change in bending moment leads to the development of unbalanced tensile forces in flanges and an unbalanced compression force at the bottom of the web. Transfer of these forces leads to the development of longitudinal shear stresses at the interface between the web and each flange. Design of the flanged beam for longitudinal shear is based on the variable strut inclination method. According to this method, the shear strength of the flange is designed by representing the flange as a system of truss cells consisting of inclined compression struts combined with tension ties made of tensile transverse reinforcement. The longitudinal shear design should assure that the inclined concrete struts do not fail in compression, while the steel ties do not fail in tension. The design procedure is based on shear stress considerations. The design stages include the calculation of the longitudinal design shear stress, VED, the check of the stress in the most loaded concrete strut, and the calculation of the transverse shear reinforcement. The longitudinal design shear stress, VED, is maximum in the regions of the maximum changes in the bending stress occurring at the steepest parts of the bending moment diagram. The change in the longitudinal force, delta Fd, can be calculated as the change in bending moment divided by the lever arm between the forces in the flanges and the web and multiplied by the ratio between the clear flange breadth and the web breadth. The force delta Fd should be transferred through the interface between the web and each flange of the beam segment with a delta x length. As a result, the longitudinal design shear stress, VED, is calculated as the force delta Fd divided by the area of the vertical section between one outstand of the flange and the web. The maximum length of the beam segment considered depends on the loading. In the case of a uniformly distributed load, delta x equals half the distance between the section with 0 and maximum bending moments. In the case of point loads, delta x should be not larger than the distance between the loads. If the longitudinal design shear stress is smaller than 40% of the design tensile strength of concrete, the concrete flange is strong enough and longitudinal shear reinforcement is not required. The angle of inclination of the concrete strut depends on whether the zone of sagging or hogging bending is considered. For flanges in compression, the inclination angle θf is in the range of between 26.5 and 45 degrees, and this results in the cotangent θf in the region of between 2 and 1. For flanges in tension, the inclination angle θf is in the range between 38.6 and 45 degrees, which results in a cotangent θf in the range between 1.25 and 1. The lower value, θf, is first tried in design. If the shear stresses are too high, θf is calculated using this expression. The following condition should be satisfied to prevent crushing of the compression struts in the flange under the applied shear. This condition accounts for the strength reduction of concrete cracked in shear. The required transverse shear reinforcement is calculated using the formula 6.21 in Eurocode 2 as the ratio between the area and spacing of reinforcing bars. Eurocode 2 requires that the transverse shear reinforcement area should be greater of the area given by formula 6.21 and half of that given by formula 6.21 plus the area of steel required by the transverse bending of the flange. The minimum transverse reinforcement is calculated using the following formula. The value of the minimum transverse reinforcement depends on concrete class. For example, for C30/35 concrete, the minimum transverse reinforcement ratio should be larger than 0.0015. Longitudinal tension reinforcement in the flange should be anchored beyond the strut required to transmit the force back to the web. Otherwise, it won't be able to carry the tension force effectively. In the case of a simply supported beam under uniformly distributed load, the biggest change of bending moment occurs at the ends of the span. Therefore, delta x equals half the distance between the section with zero and maximum bending moments, which gives fourth of the span length. The bending moment at the fourth of the span is equal approximately to 3/4 of the maximum bending moment at the mid-span. This value is the change of the bending moment in the beam segment considered. When the flange is much broader than the web, the force delta FD can be found as half of the change in moment divided by the lever arm Z, where Z is the effective section depth minus half of the flange depth. The longitudinal design shear stress, VED, is found as the force delta FD divided by the area of the vertical section between one outstand of the flange and the web. Let's consider an example. A T-beam carries a maximum bending moment from a uniformly distributed load of 400 kilonewton meters. The span is 7 meters and the effective width is 2.24 meters. The flange is 200 millimeters thick and the web is 300 millimeters wide. The lever arm Z is 641 millimeters. 12 millimeter diameter bars at 150 millimeter centers are used in the slab. The concrete strength is FCK 30 Newton per millimeter square. We start the longitudinal shear design with finding the force delta FD. In the case of a simply supported beam under uniformly distributed load, change in the bending moment equals 3/4 of the maximum bending moment, which gives 300 kilonewton meters. This then gives the force delta FD of 234 kilonewtons. The longitudinal design shear VED is 0.67 Newton per millimeter square. Now we can design the additional area of steel required to carry longitudinal shear in the slab using the following expression. In the calculations, the bar spacing equals 150 millimeters. Since we consider sagging bending, the limits for the strut inclination angle are 45 and 26.5 degrees. For the strut inclination angle of 45 degrees, the required amount of steel equals 46 millimeters square. And when the strut inclination angle equals 26.5 degrees, the required amount of steel is 23 millimeters square. At the next stage, it should be assured that the area of steel provided is greater than that is required for transverse shear, or half of what is required for transverse shear plus that is required for transverse bending. Next, we check the compression capacity of the inclined concrete strut. For the strut inclination angle of 45 degrees, the compression capacity of the strut is 4.49 Newton per millimeter square, which is larger than the applied shear stress. For the strut inclination angle of 26.5 degrees, the compression capacity of the strut is 3.59 Newton per millimeter square, which is also larger than the applied shear stress. Thank you for joining me. We've now concluded shear in reinforced concrete design according to the Eurocodes. We've now actually got all the tools to specifically design beams, slabs, and columns. And that's what we'll be doing next. We'll be looking at moment redistribution and then some specific design of beams, slabs, and columns before looking at some detailing. So join me next time for that.